So far in this topic, we've looked at what is ionizing radiation. We've looked at the three different types, alpha, beta, and gamma. We've looked at their properties. We've also looked at the idea of half-life, the fact that a radioactive substance, as it decays, there's less left behind, therefore the activity decreases with time. But we haven't really considered yet what effect these radiations have on the body. And quite frankly, they can be quite dangerous. And so, as we go through this, I'd like you to fill in the gaps in your notes, and we'll point out just a few of the significant things to consider. The problem with ionizing radiation is it ionizes. It will strip electrons off other atoms that it passes by. And that can cause a problem if it gets close to our cells, because it can start to break up the DNA in our cells or cause faults whenever the DNA replicates during cell division. And those can cause cancers. They can either kill the cell, if there's just too much radiation, it puts energy into the cell and eventually it'll kill it, or it can increase the risk of a mutation forming, which is cancer. And in general, the larger the dose of radiation, the greater the risk. Now, we've already considered background radiation. We are all constantly exposed to radiation from our surroundings, from space, from rocks, even from food. But that's a very low level and is not likely to cause significant health problems. In saying that, radon gas, which we have quite a low amount of radon gas where we live, radon gas is the UK's second highest cause of lung cancer. It's a radioactive gas that comes up from rocks, particularly granite rocks, and it will and because it's breathed in, gets into the lungs, it increases the risk of lung cancer. But normally, background radiation is a very low level, and it's not something we have to concern ourselves with too much. Now, the different types of radiations have different risks depending on where they are. We know that alpha particles have a very low penetrating power. They can't get through paper, so they couldn't get through clothes, and they can't even get through the dead layer of outer skin cells that you have in your body. So outside the body, alpha isn't a problem. However, beta and gamma can pass through the skin, and that can cause a bit of difficulty. Alpha, as we said, outside, not a problem. But if it gets inside your body, it causes a significant problem because it is the most ionizing. Remember, it has the largest charge and moves the most slowly. Therefore, it is able to lose its energy in ionizing a lot more easily than the other two. So if you breathe in an alpha particle or have some in your food, that can cause risk. One alpha particle, not so much, but a high dose would cause a problem. This is an interesting photograph. It shows Harold Agnew, who's a physicist, and what he's got in his hand there, that small case, is the core of a nuclear bomb. It's in fact the Fat Man bomb, which was only the second nuclear weapon ever used in war. It's the one dropped in Nagasaki. It's the one that effectively ended the Second World War. 6.2 kilograms of plutonium, which is an alpha emitter. If you notice there, he's not wearing any protective clothing. He doesn't have to worry about the huge amount of radiation because it can't get through his skin. It can't get out of the case that it's in either. Rather grimly, that is responsible for the death of possibly 80,000 people. That single unit there. A lot of the deaths in Nagasaki were caused by long-term deaths, long-term health effects, so leukemia and things like that, that were the result of these higher doses of radiation. Another case of alpha particles causing health difficulties is this person, Alexander Litvinenko. About 14 years ago, he was poisoned in London. A very small amount of polonium-210, which is a very strongly alpha-emitting isotope was put in a cup of tea, and within a few weeks he died from total internal organ failure. You could have a look online to see a bit of information about that. It was very prominent on the news. So if we have to use ionizing radiation, is there anything we can do to minimise our risks? Yes, there are a number of things. Stopping the radiation reaching the body is key. So one thing, protective clothing. If you're handling materials, do it remotely. Either use, we never pick up our radioactive sources in school with our hands. We always use tongs to keep them further away from our body. In industry, that could be done robotically sometimes. Minimise the amount of time you spend with the radiation. In school, we have it all locked up in a safe. We take it out for a short period of time, and as soon as we finish with it, it goes back in the safe again. It's always stored, as I said, in a safe and in lead containers to minimise the amount of radiation that gets out. Generally, shielding is one way. I'm sure many of you have had an X-ray before, maybe at the dentist or in hospital, and whereas you're exposed to the X-rays, the radiologist or radiographer or nurse or doctor, whoever happens to be with you, well, they tend to leave the room or go behind a screen whenever you're getting the X-ray. Now, X-rays are not one of our 3 ionizing radiations, but X-rays are ionizing radiations. They are very similar to gamma rays. Why is it okay for you to be exposed to it, but not the radiographer or dentist or whoever happens to be giving you the X-ray? Well, you're only getting one dose. If they were exposed to doses every single day, which is part of their job, that dose would build up and would increase the risk. So getting an X-ray for you, fine. Getting 100 X-rays, not so good. Hence, they will leave the room or go behind a shield. So fundamentally, you want to reduce the amount of time, you want to increase the distance from your source, and you want to shield, being that protective clothing or other sort of lead shielding. Are there any positives to radioactivity? Well, yes, radioactive isotopes are used in quite a number of industries. Medicine uses it a lot, and you can see a number of ways it's used there. So gamma radiation, whereas it can cause cancer or increase the risk of cancer, it can also kill cells. So targeted radiation on cancerous cells can kill those cells. And that's what radiotherapy is. And that might use gamma rays, in this case from a cobalt-60 isotope, or it could use X-rays, which are very similar. Sometimes we can use what we call radioisotopes to trace things inside the body. So you can inject or drink a radioactive material, and you can trace where the radioactivity in your body is then coming from, and that shows where that liquid has been absorbed. So for example, radioactive iodine, if it's put into the body, tumours will absorb iodine, and if you then use what's called a gamma camera to detect gamma radiation leaving the body, you can see where concentrations of this radioactive iodine have built up, and that generally might show the position of a tumour. The cell-killing properties of gamma radiation can also be used for sterilising things. Normally to sterilise something, you can heat it up or put it in boiling water, and that works well for things like a scalpel, but it does not work well for things like plasters or bandages, other surgical dressings. So the way that they're sterilised is they're put in their packaging, clean but not sterile, and then exposed to huge amounts of gamma radiation, and that gamma radiation will pass through the material, kill any bacteria or viruses, and sterilise the material. Obviously, it's similar to whenever you get an X-ray at a hospital, the nurse or doctor or radiographer will leave the room. Doctors or other health workers using radioactive isotopes have to take care not to be exposed to very, very high levels of that. So the doctor or the nurse or whoever may wear protective clothing while you the patient are exposed to these radioactive materials. Other uses include in agriculture. Food can be, like fruit and vegetables, can be irradiated with gamma rays to kill bacteria on the surface, which means that they don't decay as quickly, so they last longer on shelves. That might sound like you're eating radioactive food, but gamma radiation is very similar to light. It's an electromagnetic wave. Whenever you turn light off, well, the light doesn't hang around, it doesn't linger, it just isn't there anymore. Same idea with gamma rays. Once something is no longer exposed to gamma rays, there's no gamma hanging around afterwards. Other isotopes can be used for tracing things. So you can put a radioactive isotope into a fertilizer and then analyze sample crops that have used those fertilizers to see how much has been absorbed, and so you can trace the effects of different types of fertilizer. One common use is in industry. If you want to detect the thickness of a material, let's say you're rolling out a sheet metal or paper, if you put a radioactive source on one side and a detector on the other side, and by measuring the amount of radiation that comes through, you can see is your material thick enough or thin enough. If you get too small a reading, it means that your material is too thick because more is being absorbed, and so you can push the rollers together to flatten it out a bit more. Or if you're getting too high a reading, it means that your material is too thin, and so you can loosen out the rollers a bit to allow it to become a bit thicker. Whenever you're doing that, it's important that the source that you use has a very, very long half-life, because you don't want the half-life to be short, and therefore the activity of the source to naturally be going down, which would decrease your reading in the detector and would fool the detector into thinking that the rollers are too far apart. In medicine, however, you don't want a very long half-life for some of your radioactive medicines. If you put something into the body, you don't want a half-life of many years, because that will stay radioactive in the body for a long time. You want a half-life that is maybe a few hours, so it stays in the body long enough to get to where it needs to go and be detected, but after a few days will be down to a very, very low level. Other uses, radioactive tracers. If you want to look for a leak in a pipe, you can put a radioactive isotope into the pipe and move a Geiger-Müller tube along the pipe and see where the count increases, and that might show where a leak is. Smoke detectors in your house. There are two main types of smoke detectors, optical and ionizing, and most of the ones that you have at home are probably ionizing. And so they use an alpha source, americium-241, and if any smoke particles get into the detector, they'll be ionized, and that'll cause a little current, and that current is detected and sets off the alarm. It's a very, very small amount though. If you brought a GM tube, a counter, up to a smoke detector, you wouldn't really get any reading because alpha particles are contained inside the detector, they cannot escape.